assurance is the complete process. QC is about the product. If you mix them up, your lab results are at risk. Welcome back to the channel Learn with Sri. Today I am going to show you the exact difference between quality assurance and quality control and how to use them in the lab. Okay, let us get into it. Here I meant QC is the product. It means the final output that our lab gives to a client or patient or doctors. Quality assurance is the entire process from how a sample is collected to how the final report is produced. It includes pre-analytical, analytical and post-analytical phases. Okay, we all are aware that in our laboratories there is a pre-analytical phase, there is an analytical phase and again post-analytical phase. In the pre-analytical phase, what are the focus areas? Sample collection procedures and sample integrity. When we are looking into the sample collection procedures, patient identification is the first and most important step. Then collection timing, definitely collection timing and transport conditions, then type of sample, sample stability. These all steps we have to be more careful for getting an accurate report. After finishing the collection procedure, then we are moving to analytical phase. In an analytical phase, we are focusing testing accuracy. If you want to get an accurate report, we have to focus on calibration of the analyzer, controls, Levy Jennings chart review, sample processing procedures. Okay, these all analytical phases are in proper way, and next step we are going to post-analytical. In post-analytical, we are focusing result verification. Once the result is generated by the machine, we need to verify the result. How to check the turnaround time? Most of the standard laboratories are focusing on their turnaround time, critical value notification and documentation. Now we can discuss little detailed about pre-analytical phase. I'll give some examples. In case of potassium, because of the massive concentration of potassium inside the red cell membrane, that is, the concentration of intracellular potassium is around 140 millimole per liter, but the extracellular is only about 4 millimole per liter. Suppose a small percentage of RBC lysis, almost 25% only lysis, even though it dump their internal potassium into the plasma, that RBC is breaking and this intracellular potassium coming out into the plasma and it is accumulating in the plasma. So what will happen? Suppose a patient came with a true healthy potassium for checkup. His actual report could be 3.8 millimole per liter, but due to this lysis we released as 5.5 millimole per liter. Next, what will happen? The clinician treats with this high result. It could cause the drop of the patient's actual potassium to life-threatening low levels. So now you understood that the pre-analytical phase has an important role in a clinical laboratory. Same like enzymes, AST, SGOT. Hemolysis will falsely elevate AST. Interestingly, ALT is much less concentrated in RBC, so if you see a significantly elevated AST with a normal ALT in a hemolyzed sample, it's almost certainly a result of the lysis. Just keep in mind, I am telling about hemolyzed sample. So be careful while you are releasing such reports. Okay, just you got an idea about pre-analytical phase. Now we are going to analytical phase. Analytical phase, there are different kinds of errors: mechanical error, environmental error, chemical error, interferences. Nowadays, most of the laboratories are well equipped with fully automated analyzers. So anytime we can expect there will be some problem with our analyzers. So we will be always cautious about this. What are the mechanical kind of errors? There may be bubble in the reagent, sample probe, dirty cuvettes, aged photometers. These all may cause random erroneous reports. Then come to environmental. Maybe incubation bath temperature is more than 37 degrees Celsius. It will cause systematic errors. Then chemical. Suppose we are using expired calibrators. It may cause systematic errors. Whole run is shifted. Interference due to lipemic samples, hemolyzed samples. So for example, if the sample is lipemic, sodium level will become falsely low. So you got a basic idea about analytical phase. The next is post-analytical. It is a final stage of the laboratory process. It begins once the machine produces a result and it ends when the clinician interprets the result to make a medical decision. So in the post-analytical errors, the first and most important is critical reporting. Just imagine a critical high potassium of 7 is measured but not verified in the LIS. As it is a critical report, it will affect patients. What may be the root causes? Sometimes technician is overwhelmed with samples. Sometimes they ignore the flag. So as a troubleshooting, most of the laboratories following auto verification. There are set rules to hold only criticals. Use audible alarms for unverified results in LIS. Automated critical alerts. This is a special advantage of some laboratories. There is a kind of system that automatically notifies the doctor when a critical value is verified. Then delta check failures. So always be careful when we are releasing a report. Check the deltas. Patient creatinine was 0.8 yesterday and 4.5 today. Technician releases it. What may be the root causes? Failure to compare current result with patient history. What kind of troubleshooting we can do? Program LIS to hard stop results with a variance more than 20%. Data reporting delay. A troponin results takes 3 hours to reach the emergency department. This 3 hours is very crucial for the patient. This is due to poor workflow. So chat monitoring system should be there in each lab and identify where the bottleneck is. That's why we are following KPIs, key performance indicators. Transcription errors. Avoid typing manually. Technician manually types 0.15 instead of 1.5. There is a drastic difference. Human error during manual entry. This is the reason. Try to avoid manual entry to avoid this situation. Reference range verification. Now before starting a machine, in every lab we are doing validation verification. Reference range verification also a part of validation verification. An infant's phosphate is flagged critical high based on adult range. If we are not verifying the reference range, maybe in the LIS, laboratory information system set the range as adult, and we are resulting phosphate reports. So be careful and make sure LIS automatically pulls the correct range based on date of birth. Incomplete reporting, because especially in chemistries there is profiles, liver function profile, lipid profile, renal function profile. Like these profiles are there, iron profile. So while we are reporting a total protein without the AG ratio or without globulin, it is not complete. It is an incomplete reporting. At the time of validation verification itself, we have to make sure all calculated parameters are linked to the primary test. As we discussed, quality assurance is the entire process. Quality assurance is the entire process, pre-analytical to analytical, post-analytical. So you got an idea about quality assurance. It includes the whole process in a lab. So now you understand that quality assurance which tells us if the lab is running correctly. Now let us look at our QC, which tells us if your analyzer is giving a true result. The proper QC procedure is the backbone of our product, what we are giving to our customers. Our product is the laboratory reports. Quality control is the specific technical procedure used to monitor the performance of analytical process to detect and correct errors. QC in clinical biochemistry laboratories are a fundamental part of laboratory medicine that ensures accuracy, precision, reliability and reproducibility of the test results. Just imagine a laboratory without proper QC is unable to guarantee the reliability of their results, which may lead to misdiagnosis and inappropriate treatments. What are the importance of quality control? As a medical laboratory technologist, what you are getting, if you have any idea what is the importance of quality control, please comment to me. QC is essential in biochemistry laboratories for ensuring patient safety, preventing diagnostic errors, improving accuracy and reliability, supporting clinical decision making, meeting accreditation requirements, enhancing laboratory reputation, ensuring consistency of results. See this picture. This picture includes the importance of QC. The main objectives of QC in biochemistry labs include the accuracy of test results, as we mentioned before, to maintain precision and reproducibility, to detect analytical errors early, to monitor instrument performance continuously, to ensure consistency between different runs and days, to improve patient safety and clinical outcomes. Moreover, to comply with accreditation standards. See this picture. It highlights audits, documentation, analysis, compliance, controls, review, checklist. That means quality control is more than testing. It's a continuous improvement that ensure reliable patient results. How many types of quality control using in your laboratory? Which are they? There are mainly two types of quality controls: internal quality control and external quality control. Internal QC is performed within the laboratory on a daily basis. For IQC, we are using commercially prepared control materials. Most of the time, it includes two, either normal or pathological, or 3 levels of control materials. As a better practice, QC should run along with patient samples and monitor day-to-day analytical performance. If you are doing so, we can detect immediate errors in the analytical system and we can make sure the accuracy of patient results. External quality control is a quality assessment system in which a laboratory's test results are compared with results from other laboratories. Please give an example. There are lots of external quality controls. Example, CAP proficiency testing, BioRad, RANDOX. The external quality assurance is conducted by an external organization. They are providing unknown samples and our results are compared with peer laboratories. It's usually conducting either monthly or quarterly. Enrolling into external QC is very important because we can evaluate accuracy of our laboratory results. Then we can monitor if there is any systematic bias and we can ensure inter-laboratory comparability. The control materials what we are using should mimic human patient samples. It should be stable and homogeneous, available in multiple vials, traceable to international standards. How we are handling quality control materials? Quality controls are analyzed in the same manner as patient specimens by the same staff who is assigned to run patient specimens. Suppose I am a clinical scientist and today morning I am doing control and some other staff is processing samples. What is the meaning of this? No use, because today morning I did the maintenance of the analyzer, I did the QC or calibration, whatever it is. So I am the one knows about the mission, how is today's mission's condition, how it was performing, if there is any problem with any parameters. So the staff who is assigned to run the patients should perform the QC. For non-wave test, controls are run at least daily or more frequently if specified in manufacturer's instruction. The control should store at recommended temperatures by the manufacturer. Avoid repeated freeze-thaw. Mix properly before use. Do not use expired controls. Always follow manufacturer's recommendation. Okay, today morning we came. We did the maintenance of the analyzers. We did the QC. There were some calibrations. We finished the calibration also. Okay. Just to complete this all, then what you are doing next? Immediately we need to finish our samples. Definitely we need to finish our samples and we have to keep our turnaround time properly. But there is an important point, QC review. How this process we are doing, QC review. How we are doing QC review. For reviewing QC, we are utilizing a combination of statistical, graphical and automated digital tools. The main tools we are using are LJ charts. Okay, it is the main and basic one. LJ charts. Levy-Jennings chart is the most common graphical tool used to plot daily control values to detect trends, shift or random errors. Now our analyzers are mostly advanced one, no need to plot. Before in olden days we are taking the values and we are plotting the LJs. Exactly, now all the machines are accompanied with these all facilities. Next one, Westgard rules. A set of statistical rules applied to IQC data to determine if an analytical run is in control or out of control. Then come to sigma metrics. Sigma metrics is a powerful quality management tool used in clinical laboratories to assess analytical performance. By combining accuracy, precision and total allowable error. It helps to determine the stringency of our QC rules. Now come to Levy-Jennings chart. Levy-Jennings, this is an example of Levy-Jennings chart. It is a graphical tool used to monitor QC performance daily basis. Center line represents mean value. This is +1 deviation, +2 deviation and +3 deviation. Same like minus deviations, these all. LJ chart used to detect trends. Trend means gradual shift in values and also help to detect shift, sudden change in a mean. Then it helps to identify random or any kind of systematic errors. Westgard rules are statistical rules used to interpret QC result. Which are the common rules? 1 2s, 1 3s, 2 2s, R 4s, 4 1s and 10x are the main Westgard rules. Tell me which are the Westgard rules? 1 2s rule, 1 3s rule, 2 2s rule, 1 2s, 1 3s, 2 2s, R 4s, 4 1s, 10x. See the 1 2s warning rule. If there is a point beyond plus or minus 2 deviation, now where it is? It exceeds minus 2s deviation. If it is exceeding plus 2 deviation also, it is 1 2s rule. If there is a point beyond plus or minus 2 standard deviation is termed as 1 2s. Come to 1 3s. See this control? It exceeds 3s deviation. When a point exceeds plus or minus 3 standard deviations, the run is considered out of control. If one control value exceeds the mean, also we have to reject it. Now 2 2s. If two consecutive points are beyond plus 2 standard deviation, see this is minus 2s. Two consecutive points are beyond plus 2s deviation. Not only plus 2s, even minus 2 also. From the mean, it is 2 2s. Two levels of QC in the same run or two consecutive runs is called 2 2s. R 4s. See, one is here, another one is here. When one point is beyond plus 2 standard deviation and the following point is beyond minus 2 standard and the other point is beyond minus 2 standard deviation is termed as R4. When one point is beyond plus 2 standard deviation and the following point is beyond minus 2 standard deviation or vice versa. You can understand plus 2 and minus 2. So you run normal and high QC. Normal is plus 2.3 and high QC is minus 2.1. The difference is 4.4 ST. So it's a warning rule. For 1s, when 4 consecutive points exceed plus 1 standard deviation, 4 consecutive points, see 1, 2, 3, 4. Plus 1 standard deviation or 4 consecutive points minus 1 standard deviation. Don't consider only in positive deviation. In negative deviation also, it is considered as 4 1s. 10x. 10x. Most of the labs we can observe this 10x. Don't wait to complete 10 days. 1, 2, 3 days. then take action and solve your issue. When 10 consecutive control measurements fall on one side of the center line, above or below. See, now it is in negative deviation, minus deviation. So above or below, that means your control is not stable. You have to take action. Maybe due to calibration shift, the value is shifted, so your control also coming in negative bias. Or maybe load changed, or instrument drift, method bias or instrument maintenance may be required. So immediately solve these kind of issues. Which are the errors commonly happen in QC? There may be random error. Random errors are unpredictable variations. It mainly affect precision. Pipetting variation, instrument noise, temperature fluctuations, human handling errors. Maybe there is bubble in the QC solution, what we are allocating. Sometimes not mixing properly. Sometimes that QC material when we prepared it was not enough. Pipetting problems. These all random errors reduces precision. Scattered QC results around the mean. Guard rules violations. You can check your QC daily. Then you can understand these all issues. Come to systematic errors. Systematic errors are consistent. I told random errors are unpredictable variations, but systematic errors are consistent. Predictable deviations. It affects the accuracy of results. It causes the results to be consistently biased away from the true value. Maybe due to systematic, maybe due to calibration issues. We calibrated and it passed, but we did not check the curve. The curve may be incorrect. Expired calibrators we used. Calibration drift, maybe chance of calibration drift happened. Then reagent problems. Long time reagent was on board. Expired reagents. Load to load variation failed. Maybe load was changed and the load variation failed. So we have to find out the issues and resolve immediately. Instrument related errors. Photometer lamp was expired, faulty light source, shift in wavelength, improper maintenance, then incorrect method setup, procedural errors. So if we are avoiding systematic errors, we can reduce the mistakes and we can improve the accuracy of our result. What is shift? We already discussed about shift, drift, bias. We discussed it. So let us see what is shift. See this control. This control was going on positive bias. See, it was in one as it was like that. It was going on like this. Then suddenly it jumped from here to here. It is a shift, sudden change in mean due to either sudden failure or change in the light source, change in reagent formulation, change of reagent load, major instrument maintenance, sudden change in incubation temperature. Incubation temperature mostly affecting enzymes. Changes in room temperature or humidity, it may happen almost all the time. Failure in the sampling system. Changes in room temperature or humidity, it is very important. We have to monitor the temperature and humidity. Our environmental temperature and humidity affect our analyzer. It will affect our QC and calibration, affect our result also. Failure in the sampling system, the pipetting time, some error happened, inaccurate calibration or recalibration required. What is trend? See this trend. Trend in the word itself we can understand. It is showing some trend. It want to go up. See. Daily controls it is going up. A trend indicates a gradual loss of reliability in the test system. Maybe due to deterioration of the instrument light source. Say, gradual accumulation of debris in sample or reagent tubing. That's why we are telling follow the maintenance protocol. Gradual accumulation of debris or electrode surface. There will be precipitate accumulated around the electrodes. Aging of reagents, reagent aging. This is we will think simply, but it is an important factor we have to think because reagent has onboard stabilities there. So we have to maintain that. or before finishing the OBS, we need to consume the reagent. Gradual deterioration, light filter integrity, calibration, timeout has happened. So manufacturers recommending your timeout is over. So check the calibration. Calibration is okay or not. If required, you have to calibrate according to your institution's policy. Then bias. What is bias? There are different kinds of bias: random bias, constant bias, drift-in bias. How far the results are from true value? There will be a true value. See the mean, it is true value. So how far the results are from true value? It is the bias. It is observed. There is a true value and observed value. Check the observed value. There will be positive bias and negative bias. Positive bias means QC is higher than the true value. Positive bias means QC is higher than the true value. Negative bias means QC is lower than the true value. So the points we have to remember here is bias, trend and shift. Bias is constant error from true value. It is systematic error. Trend is gradual movement in one direction over time. Shift is sudden change into a new level. When QC results are out of range, what you will do? Your QC is out of range. What you will do? You will process the sample. Simply avoid the QC and you will process the sample. Please comment. No, never do like that. You take an alternative decision. If doctor wants report, you take an alternative decision according to your institution's policy. What all steps we have to take? Check the control material expiry and storage. Verify reagent lot and expiry date. Review instrument calibration status. Inspect maintenance logs. Check these all and repeat the QC. If required, use fresh file. Again it is failing. What you will do? You run QC 2-3 times and it is failing. What you will do? Check the pipetting technique. If there is any problem or whatever it is, you have to contact your service engineer if you cannot resolve it. So what are the home away tips today? Run normal and abnormal QC daily before reporting patient results. It's a must. To verify analytical stability, we need to do the controls daily basis and take corrective action if required. Trust but verify. You know your control is in control, but verify it. Utilize LJ charts to monitor trends over time, not just to see if the value is in or out. Apply Westgard rules. 1 3S, 2 2S, R 4S, 10x. If required, take action immediately. Document everything. Nowadays, all the labs are standardized and required a proper documentation for audit purpose or future verifications. Proactive approach. What is proactive approach? If QC fails, stop and fix it. Investigate immediately. Check reagents, calibration and equipment maintenance before testing patient samples. So we can conclude now. Quality is not an on-time achievement but a continuous journey. Through effective quality assurance and QC practices, laboratory can maintain high standards. We can improve patient safety. We can ensure regulatory compliances and deliver reliable reports. It is the important. If we are giving a reliable report to patient, it is worthwhile for them. The diagnosis will be early and patient can cure fast. Excellence in quality ultimately translates into excellence in healthcare. Thank you for watching.